Okay, Adam, take it away.
All right. Good morning. So I'm Adam Parower from the Aerospace Corporation, and today I'll be talking about a GNU radio-based full-duplex radio system. By the way, this is one of the many different research-type projects that we work on at the Aerospace Corporation. If you find this talk interesting and you're interested in working on similar projects, come check out our booth. We are hiring, so just know that we're looking for both junior and senior engineers. Without further ado, I'll get started. So today, I'm going to be talking about full-duplex radio. I will start out with some theory. I'll explain what full-duplex is, explain the problem of full-duplex, and how we solve it. In particular, I'll be talking about the theory of digital cancellation, which is an essential component of any full-duplex radio system. I'll talk about how we model the system as a black box, in particular how we model nonlinearity, and then how we can formulate that as a least squares problem, and then I'll give some algorithms for solving that problem. So we implemented some custom GNU radio blocks. I will talk about those for solving this digital cancellation problem. I'll talk about how we implemented them, and then give some results. I'll show how much cancellation we were able to achieve and how much throughput we were able to achieve. After that, I'll give some tips on the use of Edis Research's USERP products in a full-duplex radio system and some of the issues that come up in full-duplex radio, including timing synchronization and the choice of whether to use built-in or external mixers. And then I'll wrap up with some conclusions. So, what is full-duplex communications? In the literature, when people talk about full-duplex, they're not always talking about the same thing. So it's important for me to clarify what exactly I'm talking about here when I say full-duplex. What I'm talking about is a system in which you transmit and receive on the same antenna, on the same frequency, at the same time. And if you implement a full-duplex radio system, as opposed to a traditional radio system, you can potentially double the amount of throughput that you'll get in a certain amount of spectrum. And you may be thinking, well, this is impossible. I learned in from my textbook, this can't be done. And that very well may be true that your textbook told you this is an impossible problem. In fact, many textbooks still make this claim. But full-duplex radio systems have been implemented in the past few years, and so this is a feasible technology. Full-duplex can be used to replace both time multiplexed and frequency multiplexed links. So I have some diagrams here showing time division multiplexing on the left-hand side. You can see that the axis is time. So you have some time devoted to the uplink, some time devoted to the downlink, and you switch between the two. With a full-duplex radio system, your transmitting and your receiving, your uplink and your downlink are going on at the same time for the entire time. And then there's frequency division multiplexing, where you have your uplink and your downlink operating in separate but adjacent frequency bands, normally with a guard band between them to prevent interference. And with a full duplex link, you're transmitting and receiving over the entire frequency band. Both your uplink and your downlink occupy the entire frequency band, and this allows you to double your throughput. So what's the problem with implementing a full duplex radio system? Well, the biggest challenge, the primary challenge here, is self-interference. If you have a transmitter and a receiver separated by some distance, you're going to be dealing with free space path loss. That means once the transmitted signal gets to your receiver, it's going to be much weaker than the signal that's being transmitted by that same radio. And so what can happen is the signal you're transmitting can drown out the relatively weak received signal, making it difficult to detect. And so I have a diagram here at the bottom of a radio system with your transmit and receive chains showing different ways by which your transmitted signal can leak back into the receive path and interfere with your receiver. So sources of self-interference include leakage through the circulator. The signal that you're transmitting can reflect off of the antenna and come back in that way. It can go out from the antenna, reflect off of, say, nearby buildings, and then come back into your system. There can be coupling on cables that induces a signal back in the receiver. If you're using, say, a software-defined radio where your transmitter and receiver are on the same physical device, You can have leakage through that. So there are all these different sources of self-interference that we need to figure out how to get rid of. So what's the solution? Well, all solutions to this problem of self-interference that I've seen in the literature anyway depend on the fact that we know the signal that we're transmitting. So the signal that we're transmitting, as it leaks back into the receiver, it can undergo delay and distortions, and we do need to account for this in our model. But the basic idea is to subtract the transmitted signal from the received signal, and then you've removed the self-interference, you have the signal that you're trying to receive. Sounds easy, right? Well, as always, the devil's in the details. And in many cases, with a full duplex system, the signal power of your transmitted signal may be 100 dB or more above the signal that you're actually trying to receive. And so if you're looking to cancel 100 dB, you're going to need to model that signal very well. You need very high linearity, and you need accurate matching. You need an accurate model that accounts for all the distortions that are going on. And so there are two major approaches that all full duplex systems use to cancel self-interference. The first is baseband or digital cancellation. That happens usually in software. Sometimes it's implemented in FPGA, but you're doing digital cancellation, and then there's analog cancellation. So today, I'll mainly be talking about digital cancellation and how we can do that in GNU Radio. But as far as analog cancellation, the way it typically works is you tap off a little bit of power from your transmit chain. You have some sort of array of attenuators and delay lines that can be fixed or variable. The attenuators will be variable, and you can adaptively tune those attenuators so that it matches the self-interference signal, and then you can have a block which subtracts out that signal from the received signal. And so what you're doing is you're trying to minimize the power that goes back into your receive chain. So as I said, I'm going to talk about digital cancellation. I'm going to use this GNU radio flow graph to explain what's going on. So in the top left, you have a signal source. This can be anything. It doesn't really matter what type of signal you're transmitting. It could be PSK or OFDM or FM, whatever the signal is. It doesn't really matter for the purpose of full duplex. We're going to call the signal that comes out of that A. This is your transmitted signal. It's going to go out of a software radio. In this case, it's a USRP sync. Everything in the analog domain, we're just going to model as a black box. And we're going to try to figure out what's going on in that black box, how we can model that. The signal that comes out of the black box is going to be combined with the received signal, the signal we actually care about and wish to demodulate. It's going to go back into a software-defined radio. We'll call that signal B. This is your received signal, including the self-interference that leaks through the black box. And then we have this digital canceller block. This is the block that I'm going to talk about different implementations of. This block is going to look for anything that's a function of your transmitted signal A, and it's going to subtract it from your received signal B. Once you do that, we're getting a signal that I'm calling R. That's your final received signal, hopefully without the self-interference if your digital canceller is working, and that's going to go into your demodulator or whatever signal processing blocks you have down the chain. So what we want to do is find a model for this black box. We're looking to minimize that signal R, more precisely the absolute value, the norm of that signal R, which is B minus F of A, where F is your model. So this model F needs to account for the following things. It has to account for gain, since when your self-interference will leak back into your receive chain, it will likely be attenuated by, say, 20, 25, 30 dB. So you have to account for that. It's an unknown amplitude scaling. It'll likely be phase shifted. It will be delayed in time. It takes some time for the signal to, say, bounce off a building and leak back into your receive chain. There will be nonlinear distortion because you have in your chain devices like amplifiers and mixers, which we know are nonlinear. And then there's multipath interference. As I showed on the previous slides, there are multiple paths by which that transmitted signal can leak back. So For the time being, let's set aside nonlinear distortion and think, what kind of model can account for a gain, a phase shift, a time delay, and multipath interference? Well, if you're thinking of an FIR filter, you're right, that's what we decided to use. So we can model the black box here as a non-causal FIR filter. Non-causal meaning that we're going to say the received signal at the current time depends on samples from the past as well as samples from the future. And that's not a problem when you know what the transmitted signal is. So here's some notation. We're going to let A sub I be the ith sample of the transmitted signal. B sub I is going to be the ith sample of the received signal that includes the self-interference. And then X is going to be our FIR filter coefficients. So we want to, as I said before, find the FIR filter coefficients that minimize R, that is to produce R that is most similar to the actual received signal. So here I'm going to show you an example. This is a 5-tap FIR filter, which we can use to model, say, the second received sample, that's B2. Notice how B2 is depending on the transmitted signal A from both before the second sample and after. So it's dependent on samples 0 through 4. And X, again, is your FIR filter coefficients. It's going to be useful for us to show this equation in vector form. That's what I have at the bottom here. So you have a row vector containing samples of your transmitted signal A, a column vector with your FIR filter coefficients, and when you take the vector product there, your output is a sample of your received signal. All right, so what about nonlinearity? Because I mentioned before, we need to model nonlinear distortion. If you've read any of the literature about modeling, say, amplifiers or other nonlinear devices, you might have seen that these devices are usually modeled using a Taylor series. And it's usually a Taylor series with odd powers. That is the first order, the third order, the fifth order, and so on. If you do the math, you can see that the even orders are out of band, and so we can pretty much safely ignore them because they'll get filtered out by any physical system. So same notation as before. A is our transmitted signal, B is our received signal. I'm adding another subscript to X, our FIR filter coefficients. So the subscript J is going to represent the power, the order that's being applied to the transmitted signal corresponding to that FIR filter. So in this example below, we have essentially a summation of 3 FIR filters being applied to each 5 samples of the transmitted signal. You see in our row vector of A, of our transmitted signal, we have 3 different sections corresponding to the first order, the third order, and the fifth order of the transmitted signal. And then corresponding 3 sections, which are 3 different FIR filters essentially being summed together to give you the the received sample on the second sample. The problem with this equation here is we have one equation with 15 unknowns. We're trying to find our x's here, our FIR filter coefficients, so we can find the predicted value of the received signal and then subtract it from the transmitted signal to get your residual. We have one equation with 15 unknowns, and this is obviously a problem. So what do? We construct a matrix representing many of these equations. So each row of this matrix represents a model for a single sample of the received signal. You see on the right-hand side, we have a column vector of our received signal. That's our B. And now we can just extend this matrix for some reasonable number of rows, say 500 or 1,000 rows of this matrix, and now we have an overdetermined system. And now it becomes clear why I used the letters A, X, and B for this. This is a classic overdetermined system, which can be formulated as a least squares problem. We want to solve the equation AX equals B for the vector X. And so we're looking for the value of X that minimizes the norm of AX minus B. So there are several algorithms for solving such a system of equations. You may remember some of these from your college linear algebra class. So there are two categories of algorithms that I'd like to talk about. The first I'm calling block-based algorithms. Those are those that operate on the entire matrix A at once. They're effectively computing X by taking, this notation here is the pseudo-inverse, that's the plus sign, the pseudo-inverse of A, and multiplying it by the vector B. So here are some algorithms for doing that. There's SVD, QR decomposition, Cholesky, the method of conjugate gradients. So these decompositions, what they do typically is they take that matrix A and they factor it as the product of matrices that are simpler, that have special properties, that can be easily worked with to produce something that's equivalent to A pseudo-inverse times B. On the other hand, we have what I'm calling adaptive algorithms. You might know them as iterative algorithms. They take a single row of the matrix at a time, and on each iteration, they have a stored value of the coefficients X, and they'll update it. They'll nudge it slightly in the correct direction on each iteration, depending on the value of the predicted signal. And there's a couple algorithms for doing this. You may have heard of least mean squares, LMS, or RLS, that's recursive least squares. There's actually a slight mistake here. Conjugate gradient can also be implemented as an adaptive algorithm, so you can also stick that in the right-hand column. So we picked 3 of these algorithms, and we decided to implement each of them as a GNU radio block that could be used to do this digital cancellation. Before I go any further, I'd like to make a note. The GNU radio blocks that I'm about to show you are not just for full duplex. They're for digital cancellation in general, meaning you can use them to solve any sort of problem where you want to cancel a known signal that may have undergone some sort of distortion. So any known interferer suppression, these blocks can be used. All right, so we're doing this complicated matrix inversion, some computationally intensive tasks. We want to optimize these blocks for performance. Show of hands, how many of you have used the Intel performance libraries like IPP and MKL? All right, a fair number of you. So these are libraries developed by Intel. They're optimized for Intel processors. IPP is the Intel performance primitives. This is signal processing routines, image processing routines. They are vectorized. That means they give you access to the SIMD instructions that allow you to operate on multiple data in a single instruction. And then MKL is the math kernel library that's used for vector and matrix math. If you used the BLOS or LAPACK functions for math, then the API will look familiar to you. So we use the Intel libraries for vectorization, and we also parallelize our work. We divide the data that we're processing between multiple threads so that we can, again, improve throughput. All right, so I'm going to show you a little bit of pseudocode of how we implemented these blocks. This one is the singular value decomposition block. This is the implementation in pseudocode of the work function. So the signature should look familiar to anyone who's implemented a block in GNU Radio. We start out by defining some pointers. These are of type GR complex. So we have 2 inputs, 1 output. The inputs are our reference or transmitted signal. I called it A in the previous slides. And then B, which is our received signal. And then we have the output signal. So what do? The first step is to construct that big A matrix that I showed a few slides ago. So I have a function for doing that. We take the reference signal, we package it so it looks like that A matrix. And then these functions here below are MKL functions or BLOS functions. If you're not familiar with that API, these functions can sort of look cryptic to you, but I'll explain. The first letter is the data type. In this case, it's C for complex. The next 2 letters represent the type of matrix you're working on, in this case, GE for a general matrix, and then the last 2 or 3 letters are the type of function. It's like a 2 or 3 letter code. LSD here is precisely what we want. It's a one-liner that does singular value decomposition. So in one line, we can solve AX equals B. We get X out, and then there's one more step. We need to do a matrix vector multiplication. That's the next line, CGAMV. We do B minus AX to get our residual out. And so that is the received signal without any of the self-interference. So block size down here is basically the size of that matrix. It's a constant, say 512 rows of that matrix. So we consume and return that many samples. The QR decomposition block is implemented in a very similar manner. You see the same 3 pointers at the beginning, reference signal, our received signal, and our output. Again, we construct the matrix A. And then this time, so some background on QR factorization. As the name kind of hints, it factors the matrix A into two matrices called Q and R. In this case, we don't really need R. We can throw it away. But the matrix Q can be used to pretty simply compute the predicted values and thus the residual, our output. So we have the function CGEQRF that performs QR factorization, and then the one below it computes Q explicitly. There's a little second step you have to do there to actually get the values in Q. Once we have that, we do a matrix vector multiplication. We get Q transpose times B, and then that quantity can be used to compute the residual. It happens to be B minus Q times Q transpose B, so that's another matrix vector multiply and a subtraction. Again, we consume 1 block's worth of samples and output it. I'm not going to show you any code for the LMS-based block, but I will show you a block diagram. This may look familiar to those of you who have implemented or worked with least mean squares filters. So what we do is we take our transmitted or reference signal at the beginning, put it through a little block I'm calling a conditioner. That's going to output a single row of the matrix A on each iteration. I'm going to call that A vector. We take that, compute the dot product of A with the FIR filter coefficients X. That gives us a predicted value for a received signal. That can be subtracted on each iteration from the actual received signal. And that gives us what's usually called an error signal. That happens to be our output. That's the residual, the difference between the predicted and actual received signal. And then that error feeds back into this little weight update equation that will update your values of the FIR coefficients based on the value of the error. A couple things we do differently for the purpose of optimization that's not seen in classical LMS setups. We're optimizing for throughput by multi-threading. So instead of operating on one sample at a time in a sequential fashion, we take blocks of data, split them up between multiple threads, and each thread kind of does its own work until they come back together and synchronize. Also with LMS, it is not necessary to update the weights, that is the X, on every sample. You can do it every few samples, let's say every 16 samples. And then each thread does its own work. At some point, they synchronize, they're done with their data, and we can average the values of X that they come up with at the end. So here's some results. How well can our blocks cancel these signals? So we did a little digital simulation, and yes, this is purely digital, done in GNU radio. We took these blocks, just ran this little simulation, varied the SNR of the signal we're trying to transmit. So we had some known signal, we had some noise underneath it, and we're looking at how much cancellation are we able to get as we vary the SNR. So what we have on the y-axis here is the SNR of the signal after cancellation. So on this axis, lower is better. Lower is more cancellation. And what we see here is two things. One, these lines are very flat. Basically, it doesn't matter how much SNR we start with, we're able to cancel all of it, or almost all of it. And that shows that we're not running into precision issues, that complex floats are good enough to cancel pretty much the entirety of the transmitted signal, the self-interference. You also see that the LMS block performs not quite as good. You sacrifice about a dB of performance in this configuration. But what you do get out of the LMS block, and this is why we designed it, is you get higher throughput. So with LMS, we're able to get, let's say, 30 to 45 megasamples per second of throughput, depending on how many coefficients we choose to model. That represents a substantial improvement over the SVD and QR factorization-based blocks. And I should tell you that this test was done using this CPU, the Intel Xeon, with 8 threads in each block. All right, so some tips for using USRPs in a full duplex radio system. The first issue anyone doing full duplex is going to encounter is timing synchronization. For a flow graph like this to work, the source block and the sync block, the transmitter and the receiver, must start streaming data at the same time. They have to be synchronized, otherwise when the signals go into your digital canceller block, they're not going to be aligned and you're not going to be able to cancel them. So if you're using USRPs, if you've used the C++ API or if you've used GNU Radio, you'll probably know that there are functions for doing timing synchronization. Functions like set time now, set time next PPS. So these functions set the current clock of the USRP. Next PPS is you synchronize them using a pulse per second. And then there's set start time, which basically says start streaming the first sample, whether input or output, at this timestamp. So we could do one thing. We could say, generate our flow graph, and then edit the Python code that GRC generates, call these functions, but this may not be a good idea because if we make some changes to the flow graph, we want to regenerate it, suddenly all our work is gone, and we have to redo it. Is there a better way? Well, wouldn't it be nice if there was a GRC block that allowed us to embed arbitrary function calls in the generated code? If we could just drop a block into our GRC flow graph, and then when we generate the Python code, it'll automatically insert whatever function calls we want. And so we made a block like this. We called it the function caller, named after the built-in function probe block. It's very similar in its implementation. It's a GRC-only block, and it will generate for you Python code corresponding to function calls. So back to timing synchronization. If you're using a USRP, source and sync, and you call these functions, and by the way, this happens if you have a transmitter and a receiver that you're trying to synchronize, we've discovered that there's still a slight timing offset. If you do a correlation on the signal that goes out of the USRP and comes back in, you might be off by, say, 20 or 30 samples. We found that this is repeatable. You run the flow graph again, it's always the same number of samples unless you change the sample rate, and then it may be a different number of samples. This isn't that much of an issue for us. All you have to do is stick in a little skip head block to discard the first few samples after the USRP source. Another thing I'm going to talk about quickly is the use of built-in versus external mixers. So if you've used the USRP line of products, you might know something about the daughter boards. There are 2 types. There's the RF daughter boards. Those contain LO generators and mixers so that you can output at RF. Examples are the SBX and UBX boards. But there are some daughter boards like the basic RX, basic TX, the LF TX and LF RX boards that don't have these internal up converters or LO generators. They output directly at baseband or IF. And if you're using these, if you want to output at RF, you can use an external mixer. You can go to Mini Circuits or wherever, buy a mixer, and stick it in your system, and then you can output RF. And we found that there's a performance difference between using the, say, SBX boards versus basic RX or basic TX with an external mixer. And normally, this doesn't matter. So this chart here shows how much cancellation we're able to get, which pretty much corresponds to how much SNR we have. So say we have 38 dB of SNR, which is great for pretty much any application, but when you're doing something like full duplex, every dB is essential. And so I recommend that if you're implementing a full duplex radio system with something like a USRP, that you use an external mixer for optimal performance. So this chart real quick just shows two different transmitter setups, two different receiver setups, comparing the basic RX, basic TX, and SBX boards. When you have both the basic TX and basic RX boards, you get the highest performance in terms of cancellation if you're using the external mixers. So, some conclusions. We've shown that it is feasible to implement a full duplex radio system using GNU radio. You can develop blocks for digital cancellation. They seem to work well. And you can optimize these blocks using things like vectorization, multi-threading, and this will allow you to support bandwidths in the tens of megahertz. LMS, if you choose to go that route, can be parallelized. That'll give you higher throughput, and you won't be sacrificing that much in terms of cancellation. And finally, these blocks that I've shown are not just for full duplex. They can be applied to any problem you have involving suppression of, say, a known interferer. Thank you for your time. Are there any questions?
Where's the mic? Yeah, the mic, there we go. We have one question here, and the next one was somewhere over there.
Could we please navigate back to your plots where you showed your output SNR of the various methods? Yeah, that one. I'm a little bit confused why SNR of 0 dB is good, and if an SNR of 0 dB is good, why those are in negative. Is negative worse than 0? I guess I don't understand this plot at all.
Okay. So an SNR of 0 dB may be good depending on what you're trying to do. So with an SNR of 0 dB, this is like the SNR of your final received signal. Depending on whether you're using error-correcting codes, you may or may not be able to demodulate that, so you may need some additional techniques. Basically, this plot shows the difference between this is like the SNR after cancellation. The difference between the x-axis and the y-axis on this plot shows how much cancellation you're getting. So like over on the right-hand side, if you're outputting a signal with 100 dB of SNR, keep in mind this is digital, 100 dB of SNR, and your SNR after cancellation is 0 dB, you've been able to cancel 100 dB of signal.
Okay, so that's really your interference to noise ratio that you're plotting?
Yes.
Your self-interference to noise ratio?
Yes, I should have said the signal is your self-interference here.
Okay, that makes more sense. Thank you.
Okay, looking at the time, I think we have maybe one short question before the break. Someone? Okay, go ahead.
Is the transmit and receive modulation the same in this case?
So it doesn't really matter whether or not the transmit and receive modulation are the same. They could be the same, they could be different, as long as you know what modulation the transmit signal is using and you have a demodulator to process the received signal, you can do whatever you want.
And are you releasing this code?
Unfortunately, our legal team is kind of slow, and there's a lot of headache in trying to release code, so unfortunately I can't say I am.
Okay. Well, thank you very much, and also thank you to the Aerospace Corporation for being a sponsor of this conference. So another round of applause. And before you guys run off, Michelle has some updates from both the swag booth and, more importantly, the hacking challenge. So.
Yeah, swag booth, sales are brisk, so that we still have some items left. There's plenty of steins. We're out of a couple of sizes of hoodies and t-shirts, but come see us at the swag booth and we'll get y'all kitted out. So it's a little CTF update. We now have 59 teams registered. 47 of them are on the board. We're up to 34 challenges. We may roll out a few more, and we are, of course, still open for donated challenges. Ideas are not donated challenges. We're hearing lots of ideas. We're looking for complete flow graphs, instructions, and everything ready to go, just to let you know. The most solved challenge is find the CTF server with 39 solves. The least solved, besides all the ones that have not been solved yet, is the slow advertiser. It's a blue whisperer, so you should be thinking Bluetooth, maybe low energy. That's one solve so far. We have 200, as of an hour ago, 207 correct keys have been submitted out of 2,732 incorrect keys for a success rate of 7%. So looks like there might be a lot of guessing going on. And as of an hour ago, Argilo has come from behind to take the lead. Wayland Yutani Corporation was in second. Shine Micro Strong moved to third. Unconfined_U in fourth. And Spam and Eggs is still our black ribbon recipient at -10 points. All of the RTL SDRs we have loaned out have been taken for 98% of the conference. So when people turn them back in, they usually go right back out. So it's a 98% no vacancy rate at the booth. For broadcast, the broadcast challenge, the what next and what book are back on. I accidentally hid them overnight and didn't notice until about an hour and a half ago. So if you are looking for the last two challenges for the broadcast, they're back on and you can submit keys. And if you have any questions or get stuck or just want to know more or want to demonstrate something or need a hint, please come by registration. We're here to learn and have fun. It's been a blast so far. And then ham radio exams. If you are signed up for the ham radio exam, I hope you're studying and are so ready to take it because we are very excited to have this session. Sandark people are ready, and I've been warning them that we've had a lot of interest above and beyond the people that signed up in advance. The session will be on the boat. I believe the same boat that we're going to have our party on tonight, so please don't sink it or we'll have to find another place to have the ham exam. It will be, I think, on the second floor, one floor or the other, and the other floor will be the lightning talks. So you'll be very, very close. Lightning talks are here, sorry. Other floor is the DARPA workshop. Okay, so you're right next to something else. Please don't all show up at 8:40. You can drop in throughout the day. You don't have to show up at 8:40. If you've prepared for this test, it will not take you all day. I know that we blocked out like the whole morning, but just so you know, it's a multiple choice exam. If you're prepared, you can move through it very quickly. So if you want to drop in at any time during the morning until near noon to take it, that's totally okay. I didn't know if that was really clear from the schedule or not. If you have any questions about the ham exam or you had any trouble getting your FRN or filling out your 605 or you need another one, just come by registration and talk to me. We'll take care of you. Thanks a whole bunch.
Okay, so before everyone runs off, we have the lunch break now. It's again in the expo hall, and the lunch break again is extended, so you can take some time looking at the booths. So 1:45 is when we start here. We have one presentation, and after that first presentation, we will be going into a triple track where the other two tracks are the tutorials in the shell room and the EDIS-R of NOC tutorial in Del Mar. Anything else? Okay, enjoy your lunch break. See you later.